So as mentioned, I'm at the University of Tennessee, which is located in Knoxville. I'm also at Oak Ridge National Laboratory, which is about 40 miles from the university. It's very similar to Argonne National Lab. It's a Department of Energy laboratory. It's part of the Office of Science. It does open research. I also have an affiliation with the University of Manchester in England. It's about 4,000 miles away, but I don't go there very often, so that's the good news. Okay, we're going to talk about solvers and eigenvalue things. So we're going to talk about problems related to this, solving AX equal B, solving least squares problems. You want to find the minimum in some norm for solving that problem where the matrix A may not be square. We want to solve eigenvalue problems as well. So that's a major, linear algebra turns out to be a major source of computation. We're going to talk about dense problems, not sparse problems. Sparse problems are going to be addressed in another talk coming a bit later. This is about dense problems. So we have a matrix which is order n squared. It's full of data, so there are n squared elements in it. And in order to solve one of those problems there, it takes order n cubed operations, n cubed floating point operations. And this is linear algebra, occurs in many things. So here's just a list of things. That list can go on for a few pages. And we're not going to look at that list in very much detail. I'm a software guy, and I've been developing software for the past, 50 years. And I've been developing software to solve these problems here. So that's sort of where I fit into things. I've done some other things as well, but that's, if somebody was going to ask me what I do, I would say that's mainly it. A lot of other people have presented software. So there's a web page that's here, and I've collected together all the software I know about for solving that problem that's freely available. So these are software packages which you could download. And I'm making no comment on the quality of the software other than that it's freely available and it has some traction. That is, some people use it. And I've tried to list the situations where it can be used: real arithmetic, complex arithmetic, what language that it supports, if it has accelerators, if it's distributed memory, and some other things as well, and the last time the software package was updated. So it's a good source. If you click on something on the left there, you'll find the package. And you can download the package. It's freely available. You can embed it in your codes. There's a license, of course, that goes with it. Some of those licenses are very liberal. Others are more restrictive. The most restrictive one on that list is probably LGPL. And that's not very restrictive. So you can use that code freely. The web page has collected also packages that deal with sparse matrices and eigenvalue problems and all sorts of other things. So it's a resource that you should be at least aware of. And some of the stuff that's near and dear to my heart is in that package. And these are some of the things that I've been involved in over the last 40 or 50 years. Let me just make a commentary. If you have questions, ask them during the talk, because it'll make it more fun for me and for you as well. So just raise your hand if something's not clear, and we can deal with it. So we're interested in solving that. Some of you may be aware of a package called LAPACE, maybe ScalaPack. Those packages were developed in the last century, and they don't work very well today, to be honest. They were developed at a time when they were important. They served a purpose. But in my experience, every 10 years, the software has to be redone, because the architecture's changed in a very dramatic way. So I'm in a mode where every 10 years I expect to rewrite everything from scratch, from the ground up, right, developing a package. These are not small packages. These are hundreds of thousands of lines of code, and they're used by many people, and we want to provide the best we can. So on today's architectures, those packages don't work very well. They work. You get an answer. The answers are high quality numerically. But in terms of performance, they're going to suffer. So it's my goal to make packages which run at near the peak performance they can obtain on the architectures that are available today. So that's sort of where I'm going in terms of things. And those packages don't do the job. Okay, so here's a chart or a slide which has the history of my life, basically. It has the software that I've been involved in. So so the last 50 years, I've been writing software, developing software, and they have its origins in this yellow book here. This is a book by Jim Wilkinson and Christian Reinsch. So Jim Wilkinson and Christian Reinsch were pillars of the linear algebra community. They developed algorithms, and those algorithms were embedded in algol procedures in that book. And the package in the 70s called IcePack, which was developed at Argonne, was to take that algol and to translate it into Fortran. Algol, if you have any familiarity with it, it was a language which organized matrices, a two-dimensional array, by rows. Fortran organizes things by columns, and that has a major impact in terms of performance, how you access data. The project that we did in the 70s took the algol and translated it to Fortran, literally. So we got row orientation for the algorithms. Now, maybe it wasn't a big deal at that time, but it very soon became a big deal because accessing data in the wrong way causes a lot of memory references, a lot of wasted time accessing things. And that package was in some sense overshadowed by a package called LINPACK. IcePack was mainly for eigenvalue problems, but LINPACK solved systems of linear equations and least squares problems. And that package was organized by columns. So we thought we had a good strategy for getting efficient code, organizing things by columns. About this time, vector computers were becoming a thing for scientific computing. So we had a code which was running by vectors, accessing data by vectors, doing vector operations. The level 1 BLAs were just coming into play, and we structured that package around the level 1 BLAs. And that ran okay on the machines of that day. That was a pretty good package. But the architectures changed, and the changes that came about, vector computing went away, faded away, and microprocessors became the thing that we built our high-performance machines on top of. And those machines had a cache-based system. Yes?
Can you explain briefly what BLAS is?
BLAS, oh yeah, BLAS are the basic linear algebra subprograms. So the level 1 BLAS are things that work with vectors. So they're things like dot products, they're things like an AXB, a scalar multiple of a vector added to another vector, taking the norm of a vector, copying a vector, things that you do vectors with. Today, we have level 2 BLAS. So level 2 BLAS elevates that from simple vectors to matrix vectors. And ultimately, we have something called level 3 BLAS, which do matrix-matrix operations. So the packages that we have, in fact, LAPACE was structured around the level 3 BLAS, matrix-matrix operations. Because I want to reference a matrix and do a matrix operation, like a matrix multiply. A matrix multiply has the ability of taking n squared pieces of data, a matrix is n squared, and then doing a multiplication of that by another matrix. That matrix multiplication generates n cubed operations. So I get a surface to volume effect. That is, I'm taking n squared pieces of data and doing n cubed operations on it. So on a cache machine, that's ideal. So on cache architectures, that was the right strategy. So blocked algorithms, that was the thing for LAPACE. That's how it gained its strength, I'll say. And that's why it became very efficient. So in the 90s, that was the way to go. That got very efficient algorithms on those architectures. But it didn't do parallel processing. The only parallel processing that you were able to do was in a shared memory context inside of the BLAS. So if the BLAS were parallel, you got some benefit from it. So if you could do that matrix multiply in parallel, it was hidden under the covers inside of that routine that was called by that library. And then we got the benefit of parallel processing. Well, distributed memory came along. So now we have to do message passing. So all that software before has to be rewritten to do message passing. So now we're going to be using multiple processes. We're going to be using multiple processes. MPI was created about this time. And we embraced that and built a library on top of that mechanism. And that, again, did those blocked operations to be very, very efficient. Well, then later we had situations where we had many core. And the algorithms that we had didn't deal with many core very well. Many core meaning we have a chip, a socket, which has a large number of cores. And being able to effectively use that in terms of doing these computations was important. So we had a package called Plasma that dealt with that. And today, I'll just jump ahead and say we're designing a package called Slate. So Slate is a package which builds on all of that knowledge that we've built up. The numerical algorithms are solid. You're going to get good answers in terms of the numerical answers. And you're going to get efficient code because Slate is designed to run on a heterogeneous platform. So think about the machines that are coming here. So you heard probably about A21, Aurora, the machine at Argonne, the exascale machine, the first exascale machine. Oak Ridge is getting a machine, and they call their machine Frontier. And that's a machine which is based on AMD parts. So AMD multiprocessors plus AMD accelerators. So that's going to be the unit. So accelerator-based computing is a big deal. That's what all of our high-performance machines are going to be based on, and that package is going to be targeted for it. So Slate is part of the project called Exascale Computing Program, ECP. It's part of that umbrella. So we're developing that as a mechanism there. So Slate is the thing where it'll occupy the next 4 or 5 years of our time developing that. I want to take a look at performance. So we're going to take a look at how fast things run. And we're going to do that based on flops. So flops is floating point operations per second. And when I talk about floating point operations, I'm usually talking about 64-bit operations, adds and multiplies. Those are the operations we're considering. They're equal in terms of their weight. And we know about machines which are teraflops. We know about machines which are petaflops, right? We have this list called the top 500. Top 500 is the 500 fastest computers. All the machines on the top 500 are petaflop now. All the machines are executing some benchmark at a rate of 10 to the 15 or greater. Right? So anything less than that, I would say, is not a supercomputer. You got to be above that threshold. You got to be on that list to be a supercomputer, basically. And we're going to exaflop, 10 to the 18 floating point operations. 10 to the 18 floating point operations per second. That's a stunning number. I have a hard time getting my hand around that number per second, right? That's incredible on a machine. And so that's where we are. So sometimes we talk about theoretical peak performance. So that's a paper and pencil calculation. What's the cycle time? How many operations can you do per cycle? How many cores do you have in your machine? You add up all those things and you get the theoretical peak performance. And then you're going to run a benchmark. You're going to run a program and you're going to measure the performance. And that performance is probably less than that theoretical peak. Can it ever be greater? Probably not unless you cheat. So the rules are different then. So something's modified in the rules to get something greater than the theoretical peak. But just as an example, so let's say we had a Skylake processor from Intel. So that was last generation Skylake. And let's say it was 2.1 gigahertz. That's pretty slow cycle time. That single core of a Skylake can complete 32 floating point operations per cycle. Every cycle, 32 floating point operations are retired, finished. That's a stunning achievement in itself. Each core does that, 32 per cycle. So that turns out to be 67 gigaflops. So that's the rate. If you multiply all those things together, the cycle time, how many operations you do per cycle, for that single core, you get 67. And if you have a machine which has 24 cores on a chip, that's a processor you can buy, that's one of the SKUs for Skylake, you can get 1.6 teraflops. So 1.6 teraflops out of that one chip, that's the theoretical peak performance for that one chip, right? So that's sort of an impressive number in itself. Okay, so what's Intel been doing? This is sort of I sort of enjoy this chart here because they've, in the early days, Intel had their Xeon processor. The early Xeon processors did 2 floating points operations per cycle. That is, it completed 2 floating point per cycle for the early Xeon. And the same thing with the AMD Opteron processor. In single precision, 32-bit arithmetic, things usually double. So they gave you 4 flops per cycle in 32-bit arithmetic. Nehalem in 2009 doubled that. So they doubled the number of flops per cycle on Nehalem. And Westmere, so those two are part of their Intel. Intel does this tick-tock, or used to do this tick-tock thing. They don't do it anymore. So 2008 gave us Nehalem, 2010 gave us Westmere. Those processors had 4 flops per cycle. Sandy Bridge in 2011 and Ivy Bridge doubled it again. 8 flops per cycle per core. So every cycle you can complete 8 floating point operations. Haswell in 2013 and Broadwell doubled it again. 16 floating point operations per core. That's just part of the hardware. Skylake gave us 32 flops per core. So that's an impressive numbers for Skylake. 32 floating point operations per cycle per core, single precision 64. And the Xeon Phi was also of that characteristic. So Xeon Phi was a many-core chip that Intel produced for a short time and then canceled it. So that line of processors went away. Today, we're sort of here with this line of processors from Intel, and they have not doubled the flop count. Right? So we're stuck at 32 flops per cycle per core with the current processors. And that's just the way it is. And again, single precision doubles that. So it's interesting the way Intel has done that. So we got a lot of floating point operations going on here, right? Potentially. However, so 32 flops per core per cycle. If you have a cycle time of 2.6, that says each core can do 83 gigaflops, and the whole 8-core chip can reach 665 gigaflops. So that's the theoretical peak performance for that. The problem is getting the data to the processor. So you've probably heard about this memory wall business. Well, this is the memory wall. Memory wall says it takes 167 cycles to move data from memory to the part of the machine where you can do that floating point operation. 167 cycles you have to wait before you can start the operation. So in 167 cycles, I could have done 5,000 floating point operations. And the whole socket could have been doing 40,000 floating point operations. But I got to wait for that data to come. So the floating point part of the machine is idle, while the data is finally making its way through main memory, through level 3 cache, level 2 cache, level 1 cache, registers, and now we can do the operation. That's what takes 167 cycles. So we have to do something about that. We can only get high performance if we keep data in cache. So we move data once and then get reuse of that data. That's the only way to get performance. If you're moving data from memory all the time, you're dead. You're going to get, you can see the numbers there. You're going to be so inefficient, you might as well forget about using the modern processors. Use some old processor that's been around because you're not going to get any benefit. I want to take a look at what happens on my laptop. So my laptop has a Haswell processor in it. It has a dual-core Haswell. And it has a cycle time of 2.3 gigahertz. This is my laptop that I use to read email. It has Turbo Boost, which can boost the cycle time up to 3.5, sort of giving me 50% increase on the cycle time. And that happens if the conditions are right. So if I look at the conditions being right, 3.5 gigahertz, Haswell does 16 floating point operations per cycle. That's the nature of the hardware. I can't change that. That's the way it's been architected. That gets me a theoretical peak of 56 gigaflops out of that single core, 56 gigaflops. So this is the memory hierarchy of my laptop. There's a CPU, there's some cache, 6 megabytes of cache, and there's main memory, 16 gigabytes of main memory. And there's a way to get data from main memory into cache, and that link goes at 25 gigabytes per second. So that's the data movement rate. That's the fastest I can move data across that link to get it to the cache and then ultimately to the CPU. So that's my laptop. And what I want to do is to examine what happens for some very basic operations. So here's one of those level 1 BLAS routines, or actually 2 of them. One's called an AXB, AX plus Y, AXB. So we're taking a scalar multiple of one vector and adding it to another vector. And the other one is a dot product. So you take component-wise products and then add up the results of that to get an element. With an AXB, we're going to have n matrix multiplies. N multiplies. So we have n elements in X, n elements in Y. We think about multiplying those elements by alpha. X is multiplied by alpha. And then we add that to y. So we get n additions. So there's n multiplications and n additions in doing that operation. And with the inner product, it's the same sort of situation. I have two vectors. I'm going to be doing n multiplies component-wise, and then adding things up, and then finally adding it into the last scalar. So I get n multiplies and n operations. And if the machine has a fuse, multiply, add instruction, that's n of those fuse, multiply, add instructions. Let's not worry about that at the moment. The operation count is 2n. That's the operation count for this operation that we're going to be doing. Okay, so let's say we do a dot product. We're taking those double precision dot products. I'm going to make this very large vector. So the vector is going to be big enough, the vectors are big enough to fill up cache. I'm trying to do this to remove the latency that's associated with this. We got very large vectors. So the vector is of length 375,000. So that's a vector. We got two of those vectors. So 8 times that gives us two of those vectors gives us 6 megabytes. That's the size of my cache. So if I'm thinking about using cache here, so the time to move data from memory into cache, that's the data movement time, 6 megabytes divided by the rate at which I can move data, says it's going to take 0.23 milliseconds to move the data. Right? That's just the model that I'm using. And then the time to do the floating point operations, I've got 2n floating point operations, and the peak performance is 56 gigaflops. 56 gigaflops per second. So that says the time to do the operations is 0.013 milliseconds. So where's all my time going? Moving data, right? I'm moving data, 0.23. I'm doing something here which is an order of magnitude less time to do the operation. So data movement is going to be the big thing. So if I look at the total time, it's going to be, I'm going to say we can overlap some of this. So I'm going to take the maximum of the time to move the data and the time to do the floating point operations. So that's that number. And if I look at the performance I can get based on that time for those 2n floating point operations, I end up with the performance I'm capable of is 3.2 gigaflops. So that's the theoretical peak performance for doing a dot product on that processor. I can't go any faster than that. The processor is capable of 56 gigaflops, but I'm spending all my time moving data. So I'm dead in terms of the performance. So I'm getting something which is far less than an order of magnitude off of the peak performance for dot products. So if you do a dot product on this machine and you don't reuse the data, you're dead. You get very little performance. So this is a communication-bound algorithm. This is a communication-bound problem. It's not floating point. The floating point has been over-provisioned in this processor for doing this operation. So we have these level 2 BLAS operations, a matrix times a vector. Matrix times a vector has a characteristic of 2n squared floating point operations and n squared memory references. If we do a matrix multiply, and everything is square, we end up with 2n cubed floating point operations and 3n squared memory movements. So I have to move this matrix, and this matrix. So that's my data movement associated with that. But look at the ratio of floating point to memory. For doing the vector operations, it's 1 to 1. I have n, order n, floating point, order n, data movement. For doing matrix vector operations, it's 2 to 1. I've got 2n squared flops, and I've got n squared data movements. So it's 2 to 1, the ratio. So it's good. This is going to be a little bit better. We can see that already. And matrix multiply, if I can do matrix multiply, I get a ratio of n to 2. So it's that surface to volume effect. And this we'd expect to run a lot better in terms of the performance than these operations here, in terms of the rate of operations for those things. So let's take a look at our matrix vector. Matrix vector, I'm going to, again, make things big enough to fit into cache. So I make my matrix of size 860. 860 squared times 8 bytes. That says that the data is going to fill up cache. I get 6 megabytes of data. I've got a couple of vectors that I have to move along as well. So the time to move the data, the time to move 6 megabytes is the same. It's the same as we had before, so it's 0.23 milliseconds. The time to do the floating point operations, I've got 2n² operations now. I've got 56 gigaflops as the peak, so the time to move the data, the time to do the floating point is 0.026 milliseconds. So it's better than before, but it's nowhere near. We're still around an order of magnitude difference between those two. So this guy here is going to be controlling the performance that we can get. And if we do this calculation again, take a look at the total time. We're going to take the maximum of those two numbers, the data movement and the floating point, and then we take a look at the number of operations that we do, and we end up with 6.4 gigaflops. So 6.4 gigaflops is the rate that we would expect. The peak performance is 56. So you see we're far off, again, of that theoretical peak performance. So let's go one step further. We're going to do matrices. So now we have square matrices. Again, I'm going to make these matrices big enough so that they fit into cache. I've got a matrix of size 500. That's the size that we're going to be working with. So we have 500 squared. That ends up to be 2 megabytes. And we have 3 matrices, so that's 6 megabytes. That fills up my cache perfectly. The time to move the data, 6 megabytes, is the same. That's the same time to move the data. That hasn't changed. The time to do the operations, though, we have 2 n³ operations we're going to do on the data that's in cache. This is the rate, so we end up with the time to do the operations being 4.5 milliseconds. So now we're taking a significant amount of time compared to the data movement to do the floating point. So I'm getting reuse of data. That's that n³ factor in terms of the amount of operations that we're going to do on the n² pieces of data. And if we do this, this model again, we look at what we can do. It says that the performance that we can get for matrix multiply is at 55 gigaflops. That's the theoretical performance based on the model. And that's because we have the data movement going on, and we see a big difference between those two other operations that we had. So think about this. If you're going to do a matrix multiply, don't build it on top of doing dot products. If you did that, you're dead, because dot products, the peak performance for dot products is here. You could build a matrix multiply in terms of dot products, but you'd get that kind of performance. You could build a matrix multiply in terms of matrix vector operations, and you would get this performance. Don't do that. Do it this way. Build it on top of a matrix multiply, moving data into cache and getting data reuse. So this is what happens on my laptop when I actually run the code. So we're running a code out of MKL. MKL is Intel's matrix kernel library. So we're using very efficient implementations of level 1, 2, and 3 BLAS. Level 1 BLAS goes at 1.6 gigaflops, and this is what happens over different sizes of vectors. Matrix vector operations goes at 3.4 gigaflops, roughly twice that number. And matrix multiply is the one where we get the performance, 56 gigaflops, so 54 gigaflops. So that's the actual achieved performance for doing those operations. If I run on today's modern processor, a Skylake, this is what I get. So this is running on a Skylake. I'm using all 18 cores of the Skylake we have. Vector operations, all 18 cores fired up gets us 8 gigaflops. Matrix vector operations on that same thing gets us 25. But if I do a matrix multiply, I can run at rates exceeding one teraflop on that single socket. So big improvements in performance. So we want to use that, yeah.
What are you using to time operations?
Right, so that's a good thing. That's another talk. If we had time, we'd go into it. You want to be able to get at very precise timings. We usually use a tool called PAPI. So PAPI is something which looks at the hardware counters. All machines today have hardware counters. They're counting all sorts of things for us. They're counting the number of cycles that have been expended. They're counting the number of floating point operations. They're counting the number of cache misses. They're counting the number of data reads from memory. Everything like that is being counted in a set of, I'll call them, quote, hidden counters. They're not hidden. You can get access to them. So we have developed a tool called PAPI, which goes in for different vendors and taps into those counters. So if you call PAPI, you can get very precise details on the number of cycles that have been expended. And then if you know the cycle time, you can then compute the time. Yeah?
So if we change the number of cores...
I'm sorry, say again?
If you change the number of cores,
yes.
Does that ratio change?
So if in this particular problem, if I change the number of cores, these numbers here probably won't change much. that number will change a lot. So that number there is directly affected by the core count because we're running the cores at their peak performance, basically. So if I drop cores out, the performance rate goes down proportionately. Yeah.
So would you say this suggests that if possible you should try and recast your problem as a matrix vector, or sorry, matrix problem?
Excellent. So that's what we did. All the software we had was recast in terms of matrix multiplies as much as possible. And that's the story for LAPACE. That's how LAPACE was built. So we abandoned all the software that did vector operations and recast everything as much as we can in terms of matrix operations. And you can do that without increasing the operation count. So that's the other thing that's sort of at play here. You don't want to increase the operation count for the algorithm. You want to keep the operation count the same and do matrix multiply. Yeah.
Is there a reason you didn't do that before in earlier implementations?
I'm sorry,
is there a reason you didn't use these matrix operations before in your?
We weren't smart enough.
Okay.
And there wasn't a necessity. So what I mean by that is we didn't have cache-based systems.
Okay.
And cache wasn't around, so we didn't have to do it. That is, we didn't see a big hit in terms of performance. As the architectures changed, as improvements came along architecturally in the underlying systems, it sort of changes the balance in how things should be done, and that was one of the direct impacts. So data movement, at one time floating point operations were really expensive on machines. You know, people used to, so in the early days, Intel didn't have floating point on the chip. There was a coprocessor. You know, buy a coprocessor for doing floating point. And soon that became integrated. So that processor was very expensive to do the floating point. Today, the machines are over-provisioned. We have too much floating point capacity, and data movement is the critical thing. So we need to enhance the data movement, enhance the rate at which we can move data. That's the killer. All the problems that we have today in terms of performance comes about because of data movement. Yeah.
How does the L1 cache performance play into this?
L1 cache performance is important. L2 is more important. It's bigger. It really serves as the place for data. L1 is usually used for instructions, and it doesn't impact this problem as much. So L2 is the main driver for this, and then there's L3, and who knows, maybe L4 cache. Okay, so we get this incredible factor of 42 between doing matrix vector and doing matrix multiplication, the rate of execution. Of course, we're doing more operations with matrix multiply. But if you're going to build something, you don't want to build it on top of these operations here, because you're going to die in terms of performance. That's the peak performance you can get for matrix, for doing a vector operation, or that's the peak performance you get for doing a matrix vector. So if you engage in matrix vector operations, that's where you're going to sit. Matrix multiply has that potential. Okay. So the whole thing is about getting data to fit in cache, getting data reuse. If you have a matrix which is bigger than the cache, then you have to sort of cut things up appropriately. And you can do that. Think about splitting the matrix up into chunks which fit into cache. So many of the algorithms we have has a parameter which you can set, which dictates the block size that you use, and that block size drives the performance. And that's an experimental thing, right? I'd like it to be something that we would learn through some kind of machine learning thing, maybe. But today it's a manual thing that you have to set the knob for. And there are defaults, and the defaults work pretty well, but you can do better, of course. Okay, so in the early days in LINPACK, back in the 70s, things were designed by vector algorithms. This is just to give you a characteristic of how these things worked. Vector algorithm says we're going to take this vector here and basically update this red part of the matrix here to do a factorization. So I take this column and I take this row and I do what's called a rank 1 update, a sure complement. I change all the elements in red by multiplying that outer product between that vector and that row vector and that column vector. And that changes all the elements, and we go on to the next step. So there's a lot of data movement in that. I've got to modify all of those red elements. All the red elements have to be passed through the memory system into the floating point operations and then back out because they're going to be stored. So a tremendous amount of data movement in that. And the algorithms were designed to be loop level. So I've got a main thread of execution. I have this thing called the BLAS that I can do maybe in parallel. There's a loop there to do it, and then we go back and synchronize. So today, that idea while it seemed like a good idea at the time, is a terrible idea. I've got a machine with millions of cores, and I have to do a synchronization? If I think about firing up those millions of cores to do something, and they all have to come to a stop to synchronize, I can't do that. That's death in terms of parallel processing. So you don't want to do this. That's another thing that turns out to be important. In the 80s, we did this thing called LAPACE, working with blocks, matrix multiply, cache reuse. So instead of looking at one column, we did a panel. You do a panel, you think about introducing zeros in that panel and then updating, again, that red part of the matrix. That update of the red part of the matrix is a rank K update, and that's a matrix multiply. So I can actually do a matrix multiply in that algorithm, same number of floating point operations, but I'm doing a matrix multiply. So now the rate of execution goes up for that component of the operations. So that was a good idea at the time. But again, there's this idea of a loop that goes around, and in terms of lots of cores, lots of processes running, we got a problem. So that's sort of the schematic view of that algorithm. Fork join kind of parallelism, doing something, sequentializing, doing something, sequentializing. You could do something in parallel there, but then you have to come back and join at that point. In the 90s, we had distributed memory. So now we have to figure out some way to spread the data around to the processors and then coordinate communication between the processes to do the operations. And that was done in Scalapack. So we had a data distribution which basically, we thought about a logical process grid, a 2x3 process grid in this particular case, dealt out those blocks to all the processes, so we get good load balancing as the computation evolved, and did the underlying algorithms like that. The message passing went on under the covers. There was a way of doing that, and that got reasonably good performance on our parallel machines. There were some problems with that implementation, and the problems relate to, this is looking at where this is good. So it does message passing, it was worked well for clusters. It uses something called the parallel BLAs, which encapsulate both the communication and the floating point operations. So once I know how the data is distributed, I know where all the data is, and I know where I am, my process can then coordinate with the other processes to send and receive data and do the basic operations. But the problem here is that Scalapack did bulk synchronous processing. It separated the communication and the computation. So when I was communicating, I wasn't doing any computation. That was a communication phase. And then I went into a phase where I did the operations, and that becomes an issue. And again, it does this thing where we don't, we're running things on a loop level basis. So again, I have to sequentialize after every step of the process. After every, quote, iteration of the process, I have to sequentialize. And that's a killer when we have thousands of, millions of MPI processes running around. Well, today's machines are quite different than those machines we had in the last century. Machines we have today are highly parallel. They have a mixture of MPI and OpenMP. That's the way we're designing our codes today. They're heterogeneous. They have commodity processors plus an accelerator tied to that. So we have a node. On that node are a bunch of sockets. Those sockets have a multi-core, and they also have accelerators. Perhaps a number of accelerators on a node, and we have to coordinate that. So think about nodes on the order of thousands of nodes in the machine. Think about the total core count as being in the millions of cores that are coordinating things. And in terms of MPI, the nodes are the things which are the MPI processes. And within a node, then we're going to do some operations, and that operation is basically the kinds of things I've been talking about here. Going the wrong way. Simple loop level parallelism is too limiting in terms of performance. Again, it's that fork join. You can't have that synchronization point. Synchronizing thousands of MPI processes just puts everything to a halt while we wait for the slowest one to complete, and that really doesn't hold up. Communication is expensive, and we have to really come to terms with that communication. I'm not going to talk about it here, but my colleague Jim Demmel is going to be talking about communication avoiding algorithms. Algorithms that try to minimize the amount of communication. that come up with theoretical lower bounds for communication within a given algorithm and trying to design that. And the other thing to keep in mind is that the number of operations may not dictate the time to solution. So I could have algorithms which do more floating point operations and they take less time than a more conventional one. So the number of floating point operations in your algorithm may not be a good reflection of time to solution. So if I have two algorithms which are doing the same problem, one having more operations, it may be, in fact, better to use that algorithm in terms of time to solution than the other algorithm, even though it does more floating point operations. And today, we're looking at machines which have different levels of floating point capability. So we know about double precision, 64-bit floating point operations. We know about single precision, 32, but machines today have 16-bit floating point operations. So there's an IEEE standard for 16-bit. And you get a factor of 2 going from each of those. So 16-bit floating point could be 4 times as fast as the double precision operations. And certain manufacturers have accelerators which can make those 16-bit operations, in certain cases, run 10 times more effective. And those operations are matrix multiplies. So this drive to lower precision is being encouraged by machine learning. So machine learning algorithms don't need the kind of precision that we normally think of for solving three-dimensional partial differential equations, which most of the machines we have are used for. And 16-bit is being put into the hardware. We get it, and now the question is, can we use it? Can we effectively use 16-bit floating point? So let's just take a look at an algorithm. This is an algorithm that was in LAPACE. It's what we call a right-looking algorithm. It's based on a panel. This is a panel. That's that panel there. And we do an operation. This is a triangular solve, and then we do a rank K update, a matrix multiply based on that. That's the way it would look in the LAPACE routine. There are routines that are called, these guys here are BLAS routines, level 3 BLAS routines that are called to do that, and it runs okay. But it has some deficiencies. This is the way it's being designed in Slate. We're taking that algorithm and making it more tiled. So we think about breaking things into smaller tiles and doing those operations. And this is the way the operations would could be described for that algorithm in terms of working on those tiles. The tile size is something you can control. There's a dial on doing that. Maybe it's 64, maybe it's 128, maybe it's some other number. And of those two algorithms, the algorithm on the right has a better chance of running and running more efficiently than the guy on the left. This is looking at the dependencies between those blocks. This is in the LAPACE algorithm. These are the dependencies. That is to say, this operation here, which is a multiply, has to wait until this guy finishes and has to wait until this guy finishes, just if you draw it out. These dotted lines here represent loops in the program. And things are sort of organized so that these blue things are one triangular solve. This is a matrix multiply that's taking place. This is another kind of component in the algorithm. And you can see the data dependencies there. That's a directed, that turns out to be a directed acyclic graph for the algorithm. In Slate, I can do a reordering of that. I can reorder the blocks here. I can basically get rid of these barriers between loops and push things higher up into that graph to get something which is correct. It gets the same answer, but it does things in a slightly different order and runs faster. So the number of cycles it would take is reduced. In this case, it looks like 2, but in larger cases, it's much larger improvement in terms of the performance that you end up with. And there's a critical path there. So executing that critical path is important. If you do that, you release as much parallelism as you can, and the problem will run even faster. So loops are basically eliminated in this implementation here. They're still there in some sense, but the loop boundaries are not respected in terms of the execution. What's respected is the data dependencies. So we're trying to get at a point where we just look at the data dependencies between those blocks. So think of it like this. The algorithm basically generates a DAG, that directed acyclic graph. It generates all the dependency information. And then on the other side is an execution phase where we execute that DAG, looking at the dependencies and trying to execute whatever's ready to execute as soon as possible. So that's the model that you should have in mind. So that's the way the algorithms are being constructed today. And that helps to release that loop level business and drive things more towards the asynchronous flow. So the algorithms in the old days looked like that in terms of the execution. Today we have, if I was going to draw things, a DAG would look something like this for the execution graph. The old way of doing it generated a trace. This is on 64 processes, or maybe 16, I don't remember the exact number. And time is running across there. Yellow, or the coloration is work that's going on. The gray is idle time in a given process. And the old way of doing it, we could literally see the loops that are executed there in the program. If you do this DAG-based thing, you end up compressing that, getting rid of that synchronization, and allowing things to run in a more natural way, doing things in this sort of asynchronous fashion, sort of out of order, and ending up with an execution which is a significant improvement in terms of performance. So that's what's happening with the Slate library. That's what we did in a library called Plasma. Sometimes we need to put routines together. So this is an example where we're going to compute the inverse of a symmetric matrix. It's probably being used for a variance-covariance situation where you need the exact inverse, the X elements of an inverse. You do a Cholesky factorization, you do the invert you invert one of those factors, and then you multiply it by itself to get the inverse of the matrix. So we have 3 routines we're going to call. Each of those routines have a DAG associated with them. And each of them has if you're going to run it on a machine, it could look something like that. This is run on a Intel Xeon Phi, I think, with 64, 68 cores in it. So it looks something like that. Each phase looks something like that. And what we notice here is each routine is doing okay, but we see a lot of space between that before the next routine starts. We have these DAGs available to us. What if we put the DAGs together between routines? We could end up with a DAG which looks like that. So that's the merger of those 3 DAGs between boundary lines of the routines. And the execution flow then for that says we're going to run something like this, where we get rid of a lot of that white space, compress things, and the actual time to solution is much, much better with this implementation. So that's the structure that we're dealing with today in terms of these machines. And that's the way the library is being designed.
Excuse me?
Yes.
For the previous slide, I think I missed what you said. So the top
I'm sorry,
thing,
going backwards. Okay.
the top one has the DAG applied, but just for each of the pieces separately.
Yeah, that's
Okay.
exactly right. Yeah, and we have a way of taking those 3 DAGs and basically smushing them together, and that smush looks like that, and that ends up with a much more efficient data flow associated with it. So we basically get the data flow for the 3 routines put together rather than each routine individually. Okay, I mentioned something about machine learning. Machine learning is a big deal. A lot of attention's being applied to it, and for good reason. So machine learning is going to be it's going to be a tool that we use. Computational scientists are going to rely on machine learning to help solve the problem. They're not going to be solving the problem with it, but it's going to help them along the way to solve the problem. And we should learn about it and use it and make it run as efficiently as possible. So one of the things in machine learning is matrix multiply. They have lots of matrix multiplies that they have to do. We see this and we recognize that it's an important thing. And in our algorithms, we have that same situation where we have a number of times we see operations being repeated in a sequence, and sometimes those are small-ish operations. For machine learning, the matrix multiplies are really quite small that we have to deal with. And we want to put together a mechanism so that it's dealt with efficiently. So think of it like this. Here's a matrix multiply that I'm going to be calling in a loop. Each of these are distinct and different, and I've got a processor over there that's going to execute it. If I do it the way I might be thinking, I would take one of those matrix multiplies, run it on that machine, but that machine, that chip, that processor, it has excess capability. It has a lot of ability, but I'm not using all the cores, for instance. So then I get the next guy and the next guy and the next guy, but I'm wasting a lot of that processor. What I would like to do in this situation is to take all of those operations and push them into that processor. So I have a batch of them. I have a framework for dealing with the batch. One call says I'm going to do this batch, thousands of matrix multiplies. And I have I think of on the back end of that call, I have a manager that's going to manage that work when it's given to it and schedule it on that processor. So that when I invoke that one routine to do that batch of matrix multiplies, again, it's one call with a calling sequence which contains thousands of matrices perhaps, or pointers to them. Those guys get scheduled on the appropriate computational device, and we get much more effective use of that computational device as a result of that. So machine learning needs it for doing matrix multiply. We need it in our matrix algorithms because we have this particular pattern. We have a Schur's complement that we want to compute. We have this column of matrices, this row of matrices that have to be multiplied together to update all of these matrices here. So that's the same situation. I make one call to affect that, and that can run very efficiently on the underlying architecture. How efficiently? Well, here's a graph to show that. This is on a Xeon Phi, so this is a 68-core Xeon Phi. If we have this, if we do it the conventional way, so I'm looking at these are the number of matrices that I have to deal with. I'm sorry, this is the size of the matrix, 64, 256, 512. And this is the number of matrices, somewhere between 500 and 1,000 matrices are being batched for each of these. If I take a look at running it sequentially, each of those matrices being pushed through, I get a curve which looks something like this. So if the matrices are order 512, I get that kind of performance out of it. If I think about batching this together and running those things as one call, doing 1,000 of those matrix multiplies of size 512, I end up with something which runs at this level of performance here. Right? So I'm going to be getting something which is considerably more efficient in terms of the operations. So there's a standard that we have for doing batched operations. Yes?
So at runtime, at what point is a decision made by the software to figure out what regime to run it?
Right. So it's dynamic. It happens at runtime. If it sees the matrices are large enough, it'll use the other algorithm. It'll use the more conventional algorithm. Otherwise, it uses this batching phase where it tries to do multiple things simultaneously on the underlying hardware. But that's a dynamic decision. And the user doesn't have to worry about that. That's the important part. So the user does a batch call. He's got this sequence of operations, and it's handled by the underlying software to do the right thing. And that doesn't just extend to matrix multiply. It does for all of the matrix operations that we think of. Things like singular value decomposition, eigenvalues, systems of equations. They can all be batched. Okay, machine learning's a big deal. It affects a lot of areas. You're going to hear about it if you haven't already. Machine learning uses matrix multiply, and they can get away with short, small matrix multiplies in the process of doing business. And they can do 16-bit floating point operations. Okay, so here's a joke. It says this is your machine. This is your machine learning system? Yep. You pour data into the big pile of linear algebra, then collect the answer on the other side. And what if it gives you the wrong answer? Well, just stir the pile until you get the right answer. So it sort of works like that. It's a bit mysterious to me exactly how you do things, but you get the right answer eventually, or somebody gets the right answer eventually. Okay, so we have hardware that's being built to do 16-bit floating point operations. AMD has hardware to do it, very impressive. This thing just stopped working. Very impressive performance that we see out of AMD. NVIDIA does it. You know, if you do tensor cores, is their way of doing 16-bit floating point operations. It's a matrix multiply, a 4x4 matrix multiply. You get very fast, very high performance floating point operations. So we have half precision is 16 bits. You have a sign bit The IEEE defines it to have an exponent which has 5 bits, and 10 bits is used for the fraction. That 5 bits for the exponent says the maximum number you can have is 65,000. If you go above 65,000, you overflow. So now you got to worry about the dynamic range of your numbers. Yeah?
But this batching, is it implemented in which library? Is it in the latest?
Batch, it's well, we have a specification which says we have the batched routines. Here's what the syntax and semantics are for that. So that's a standard. And then we have implementations that are available in C, Fortran, or C++. And that's all, that's a separate library, and those libraries are going to be used by Slate.
But it's not in MKL. Like,
It's not in MKL yet, but they're going to do it. They're part of the defining of the standard. Okay, so that's the IEEE way of doing half precision. The Google has something called bfloat16. They went a different way. They have 16 bits, but they're distributing the bits in a slightly different fashion. They distributing their bits. That's not the right slide. This is the bfloat. This is the IEEE way of doing business. 64,000 is the largest number. This is the way 64 bits looks. This is the way bfloat. Sorry, this is the way single precision looks, and this is the way bfloat16 looks. So with Google's bfloat16 on their TPU, they do a sign bit, and they do 8 bits for the exponent and 7 bits for the fraction. So they're doing the same number of bits in the exponent as single precision. So they have a very large dynamic range. But the fraction, the accuracy that you have is much less. So that's something to be worried about. So those are two, I'll call them competing standards for 16-bit arithmetic. And I'm running out of time, but there are really some cool algorithms you could do with 16-bit arithmetic. And that's really an open area, I would say, is trying to exploit 16-bit arithmetic in our numerical computations. So I think of it this way. I want to be able to get an approximation, and I want to get the approximation quickly. And I can do that maybe with 16-bit arithmetic. And then once I have the approximation, I think about a mechanism to get me to the full accuracy I deserve by doing some iteration and getting to that point. So I don't have time to talk about it, but there's a lot of cool algorithms, some neat things being done along those lines. So that's something which is open problems. So if you're looking for open problems, open research problems, it's right there in front of you, in front of us. So let me just go to my conclusion slide. If I could find out my cursor, there it is, thank you. Okay, so it's an exciting time to be involved in high performance computing. There's a lot of interesting things going on, and it's an opportunity to really exploit many of the things that we've learned. I'm looking for my last slide, there it is. Okay, so Plasma, Magma, Slate, the package I talked about, those are available today. There's a runtime system that we have. The work that I've talked about is funded by Department of Energy. We get help from a lot of places, NSF, the vendors give us some help. I have colleagues at the University of California, which you're going to hear about, the University of Colorado, which you won't hear about, and we're looking for good people at Tennessee. So if you're interested, send me an email and we can talk. So let me end there. Thank you so much for your attention, and I'm happy to answer any questions that you might have remaining. Yes?
So going back to the place where you merge different DAGs,
Yeah.
I was wondering how do you get that logic, the DAG merging logic? Can you explain the process behind that?
Well, think of it like this. There's a mechanism which handles all the tasks in a given routine. So that routine is, so the routine really generates the DAG. It doesn't do the execution, it generates the DAG. Then there's a runtime system which does the execution. Now think about stopping the execution from taking place and pulling on the next routine. So it generates the next DAG. And those DAGs have a connection. So when the runtime system sees them, they only know about the dependencies, and the subroutine boundary is removed so that they actually look like the same in being in one routine. And then a third routine is done that way as well. So as long as there's a dependency between it and knows about the dependencies, the runtime system is able to execute that in a very transparent way.
How are the dependencies computed?
Input and outputs. So it's very simple. I have a routine. I specify what the input and output is. If it's input, output, and then so it's automatic. Yeah, that happens automatic in the sense that the user specifies that, and then the back end takes care of the dependencies based on that information that you provided. The user, yeah.
So with can the user provide like so you get this example using Cholesky to find an inverse, right?
Yeah.
Can I provide, say, I want SVD, but on the, I want to do this, and I want another component to do this, and then you construct a DAG and then efficiently do it.
Yeah. Yeah.
So it's like, okay.
So that's exactly the way it happens. Inside of that routine, as long as the data is known, how the data is distributed and all the other things, that DAG can be constructed, be between boundaries.
Runtime or?
That's a runtime. That's a runtime. Absolutely. Yeah. So the DAGs. The other thing that I should maybe let you in on is the DAGs are enormous. So I can't generate the whole DAG and then do the execution. So that doesn't happen. What really happens is I generate a window of the DAG, and then I execute the window of the DAG, and the window rolls down. So I can't store the whole DAG is the point. If I could, I would do the critical path. Yeah.
You know that the DAGs are optimal.
So it's optimal. So again, the DAG is just representing the inputs and outputs. And you specified that. The user specifies it. So we're not doing any magic here. The user specifies that. Now the question is, do you optimally execute that DAG? And you can optimally execute it if you get the critical path. Critical path's the longest path. And by optimal, I mean it frees up the most parallelism.
Okay, so like this Cholesky DAG,
Yeah.
How did you generate that?
That's generated automatically by the program. The program does it. So think of it this way. Every call to one of those tile routines generates a call to the tile routine with inputs and outputs. That's a component of the DAG. That's a node on the DAG. The arrows going into it are the inputs. The nodes going out of that are the outputs. And that's it. It's that simple. So there's nothing magical there. And it's a directed acyclic graph. It's not a tree. Yeah. It's a very simple idea. It's an old idea, by the way. These ideas are ages old. These are not in computer science. We did this 30, 40 years ago. Now's the time. This is important now. It wasn't that important before. Yes. Yes.
I'm sorry if you already said this, but so like at Argonne we have MKL. Is your software independent of MKL, or?
So I'm not quite sure what letters you use. MPI, MKL. Which letters did you use? MKL. So MKL is the Intel kernel thing. MKL is an implementation of, for the BLAs, they've implemented the standard. So they have a library which does the standard. We write our routines in terms of that standard. So when I make a call to dgem, which is the matrix multiply, I'm happy to use the MKL one because it'll be the fastest if I'm running on an Intel platform. If I'm running on an AMD platform, I use their version of dgem, which they have. Right? But I have my own implementation. 15 years ago, we did a project called Atlas. If you want to look back historically, look at Atlas, because it was a machine code generator. It generated code based on running tests, empirical generation. Really cool project. That was before we had very efficient ways of doing it. Anything else? Yes, please.
I'm really excited about DAGs. How do I get them into my life?
Yes, how do you? Yes, that's a question, I agree. How do you get them in? So you need, with the DAG, you need a runtime system to execute them. So DAGs, OpenMP, the standard OpenMP has a mechanism for generating DAGs and executing them. So we use, on a shared memory machine, we use OpenMP to do that. We used to have a system we built ourselves called Quark, and that was before the standard, before OpenMP had a standard way of doing task-based things. But if you look in the OpenMP standard under task-based stuff, you'll see a way of doing it, and then they take care of the scheduling. So you define what the tasks are, you define the DAG based on the routine, the inputs, outputs, and then it'll manage that for you. So that's the right way to go with that. Yeah.
So sort of in the previous versions of software, you could write it all on Fortran and it runs everything, right?
That was last century, yeah.
So what do you guys do now to deal with the fact that you have to run on all sorts of different things, right? Do you just rewrite your routines for every system? Or?
Good heavens, no. No, so, so what we do is our software now is written in C++. There's a binding, I'll say, to Fortran if you need it, or C, or some other language. We haven't done other languages, but we can define a binding that is a calling sequence in Fortran, which targets the routines that we've written in C++. So that the user, if they have legacy codes, they can use our stuff. We also have a binding to LAPACE. So the stuff I've mentioned is part of, a lot of people use LAPACE and ScalaPack, and we appreciate that. And we want to be sure that new users don't have to go through a lot of rewrite to get to our stuff. So there's a way to get to our stuff by using their old calls to LAPACE. It'll bind into it.
Yeah, I mean, I guess what I mean is C++ at the moment doesn't have direct access to any sort of GPUs or anything built in, right? So
Oh yeah, right. But C++ is just a framework for writing the code, and then we write we call a routine which does the GPU stuff. So that's stuff that we call, and so we know about accelerators, we know about what I'll call commodity cores, and so that's the separation. And then we expect the library to be written on the machine to do the basic operations, and we then call their routine to do the basic operations. We expect the manufacturers to write at a certain level interfaces to our routines, and they've been pretty good about doing that. Yes?
How do you launch the batch jobs on GPUs?
Again, it's done under the covers. So you make a call to a batched routine, and that's executed. And if you have a GPU and the code has been written correctly, so the code has to, the underlying code, not your code, but the underlying batched routine has to know there's a GPU there. It will then do the scheduling on the GPU. So it should be transparent to you. It just has to, somebody has to have written the batched routine to know about the GPUs on the machine.
So is it launching multiple kernels under the hood, or will it launch one kernel, or would it submit one job to the GPU?
So that's a detailed that's an implementation issue, but usually it's one call that's made under the hood to do that, and it's managing all of the batched routines. So it makes one call, and it may make other calls after those complete to finish out all the stuff that it has to do. Okay, I think I have to cut it off because we're running out of time. I apologize for my next speaker for taking a few minutes out of his schedule, but I'm sure he'll just go a little bit longer, and it'll cut the break short. So thank you.